What if the Big Bang was never the beginning? What if the explosion that supposedly started everything was actually just a chapter break in a story so vast it makes the known universe look like a single grain of sand on an infinite beach? Most people alive today were taught a clean, simple origin story 13.8 billion years ago. Everything erupted from a single point of infinite density, and the rest is history. But the deeper physicists dig into that moment, the more cracks appear in the narrative. The singularity at time zero is not a triumphant explanation, but a confession of ignorance. A place where every equation we trust falls apart. And now, armed with the most powerful telescopes ever built, radical new mathematics, and observations that keep defying expectations, scientists are peeling back the curtain on what may have existed before the Big Bang. A realm where time itself might loop, bounce, branch, or simply lose all meaning. The answers emerging from the frontier of cosmology are stranger than any creation myth humanity has ever invented. And they carry implications not just for physics, but for what it means to exist at all. The standard cosmological model tells us that the universe began 13.8 billion years ago in an event called the Big Bang. At that instant, all of space, time, matter, and energy came into being from a state of unimaginable heat and density. The evidence for this picture is overwhelming and has been accumulating for nearly a century. In 1929, the American astronomer Edwin Hubble observed that distant galaxies are moving away from us in every direction, and that the farther away a galaxy is, the faster it recedes. This relationship, now called Hubble's law, was the first observational proof that the universe is expanding. If the cosmos is getting bigger today, then running the clock backward implies it was once compressed into a much smaller, hotter state. The logical endpoint of that rewind is the Big Bang itself. Decades later, in 1965, two American radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, accidentally stumbled upon a faint hiss of microwave radiation coming from every direction in the sky. No matter where they pointed their antenna, the signal persisted. What they had found was the cosmic microwave background radiation, or CMB, the afterglow of the Big Bang. This radiation was released about 380,000 years after the initial explosion, when the universe had cooled enough for atoms to form and light to travel freely for the first time. The CMB is essentially a baby photo of the cosmos, and its discovery earned Penzias and Wilson the Nobel Prize in Physics in 1978. The temperature of this radiation is remarkably uniform across the entire sky, measuring approximately 2.725 Kelvin, just a few degrees above absolute zero. Exactly what theoretical models had predicted for a universe that has been cooling and expanding for billions of years. But here is where the standard story starts to buckle under its own weight. The Big Bang theory is extraordinarily good at describing what happened after the initial explosion. The synthesis of light elements like hydrogen and helium in the first few minutes. The gradual formation of stars and galaxies over hundreds of millions of years. The large-scale structure of the cosmos as we observe it today. What the theory cannot do is explain the explosion itself. At time zero, the mathematics of general relativity, Albert Einstein's monumental theory of gravity, produces what physicists call a singularity, a point where density becomes infinite. Temperature becomes infinite, and the curvature of space-time becomes infinite. At a singularity, the equations do not give wrong answers, they give no answers at all. They simply break down. This means that the Big Bang theory describes the aftermath of creation, but is utterly silent about the act of creation itself. It is as if you found a detailed diary that begins on page 2, with page 1 torn out and missing. Everything from page 2 onward is meticulously recorded, but the most important page, the one that would tell you how the story actually started, is gone. The singularity problem is not merely an aesthetic blemish on an otherwise beautiful theory. It represents a fundamental boundary of knowledge, a point beyond which the physics we have mastered simply cannot penetrate. Stephen Hawking, the legendary theoretical physicist who spent most of his career at Cambridge, once compared asking what happened before the Big Bang to asking what lies north of the North Pole. In his view, time itself began with the Big Bang. So the question of before was literally meaningless, like asking for directions to a place that does not exist on any map. For decades, this was the dominant position among cosmologists. The Big Bang was the ultimate boundary, the edge of the map, the moment before which there was no before. But not everyone was satisfied with that answer, and as the decades passed, more and more reasons emerged to suspect that the story might be far more complicated. The first serious cracks in the simple Big Bang narrative appeared in the form of several puzzles that the theory, on its own, could not solve. The most famous of these is the horizon problem. Look at the CMB radiation coming from opposite sides of the sky, from regions of the universe that are now tens of billions of light-years apart. These regions have almost exactly the same temperature, differing by only about 1 part in 100,000. For these regions to have reached the same temperature, they would need to have been in thermal contact at some point, exchanging energy and heat until they equilibrated. But according to the standard Big Bang timeline, these regions were never in contact. The universe simply has not been around long enough for light, or any signal traveling at the speed of light, to have crossed from one side to the other. So how did opposite ends of the cosmos know to be the same temperature? It is as if you walked into two houses on opposite sides of the country and found their thermostats set to the exact same reading, down to the thousandth of a degree, even though the homeowners had never communicated with each other. The second puzzle is the flatness problem. The geometry of the universe, whether it is curved like a sphere, curved like a saddle, or flat like a sheet of paper, depends on the total density of matter and energy it contains. Observations show that the universe is extraordinarily close to perfectly flat, meaning its density is at or very near the so-called critical density. The trouble is that this balance is wildly unstable. In the early universe, even the tiniest deviation from critical density would have been amplified over billions of years of expansion. If the density had been just a fraction higher, the universe would have collapsed back on itself long ago. If it had been a fraction lower, the universe would have expanded so fast that galaxies, stars, and planets could never have formed. The fact that the universe is still so close to flat today, after 13.8 billion years of expansion, means that the initial density had to be tuned to the critical value with a precision of roughly 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. No natural mechanism in the standard Big Bang model explains why the initial conditions were so impossibly fine-tuned. There are other puzzles too. The magnetic monopole problem asks why we have never detected magnetic monopoles, hypothetical particles that carry only a north or south magnetic pole. Even though many grand unified theories of particle physics predict they should have been produced abundantly in the extreme conditions of the early universe. The matter-antimatter asymmetry problem asks why the universe is made almost entirely of matter, when the known laws of physics treat matter and antimatter almost symmetrically, meaning the Big Bang should have produced equal amounts of both, which would then have annihilated each other, leaving behind nothing but radiation. The fact that we exist at all, that there is something rather than nothing, requires some mechanism that tipped the scales ever so slightly in favor of matter over antimatter. And the standard Big Bang model does not identify what that mechanism was. These puzzles set the stage for one of the most important developments in modern cosmology, the theory of cosmic inflation. In 1980, a young physicist named Alan Guth, then working at the Stanford Linear Accelerator Center in California and later at the Massachusetts Institute of Technology, proposed a radical addition to the Big Bang story. Guth suggested that in the first unimaginably tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, far more violent than the ordinary expansion that followed. During this inflationary epoch, which may have lasted only about 10 to the power of negative 36 seconds, the universe doubled in size at least 60 times over, ballooning from something smaller than a proton to something larger than the entire observable universe today. The driving force behind this expansion was a hypothetical quantum field called the inflaton field, which filled all of space with a tremendous amount of energy stored in a kind of false vacuum state. As the inflaton field decayed, it released its energy as a flood of particles and radiation, reheating the universe and producing the hot, dense state that we traditionally associate with the Big Bang. In this picture, the Big Bang was not the beginning of the universe but rather the end of inflation. the moment when the inflating field dumped its energy into ordinary matter and radiation. Inflation elegantly solves the horizon problem, because the regions of the universe that appear disconnected today were actually in close contact before inflation blew them apart. They had time to reach the same temperature before being stretched to opposite sides of the cosmos. Inflation solves the flatness problem because the exponential expansion stretches any initial curvature to near-perfect flatness, just as inflating a balloon smooths out wrinkles on its surface. A small patch of a curved surface, blown up to enormous size, looks flat to any observer standing on it. And inflation solves the monopole problem because any magnetic monopoles produced before inflation would have been diluted to undetectable levels by the enormous expansion. Most remarkably of all, inflation provides a natural mechanism for generating the tiny temperature fluctuations observed in the CMB. During the inflationary epoch, quantum fluctuations, the inherent randomness and jitteriness of the quantum vacuum, were stretched to cosmic scales. These fluctuations became the seeds of all the structure we see in the universe today. The slight overdensities that gravity would later amplify into galaxies, galaxy clusters, and the vast cosmic web. The statistical properties of these fluctuations, their spectrum, their distribution, their correlations across different angular scales, were measured with exquisite precision by NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, which was launched on June 30, 2001, from Cape Canaveral, Florida, and later by the European Space Agency's Planck satellite, launched in 2009. Both missions confirmed that the pattern of fluctuations in the CMB matches the predictions of inflationary models to a remarkable degree. This is one of the most precise agreements between theory and observation in all of science, and it has cemented inflation as a central pillar of modern cosmology. But inflation, for all its successes, does not close the book on the question of what happened before the Big Bang. In a sense, it just moves the question one step further back. If inflation preceded the Big Bang, then what preceded inflation? What set the inflating field into its high-energy state? What triggered the exponential expansion? The mathematics shows that inflation cannot have been going on forever into the past. In 2003, physicists Erwin Borde, Alan Guth, and Alexander Vilenkin proved a theorem, now known as the BGV theorem, demonstrating that any universe that has been expanding on average throughout its history must have had a beginning. Even an eternally inflating multiverse, where inflation continues indefinitely into the future, producing new pocket universes without end, must have started from some initial state. The BGV theorem does not specify what that initial state was, whether it was a singularity, a quantum fluctuation, a bounce from a previous universe, or something else entirely. But it does imply that the question of ultimate origins cannot be escaped simply by invoking inflation. This brings us to some of the most provocative and speculative ideas in all of physics. The hypotheses about what might have existed before the Big Bang. One of the most dramatic is the Big Bounce hypothesis, which proposes that the Big Bang was not a moment of creation from nothing, but rather a transition from a previous contracting universe. In this scenario, a prior universe collapsed under the pull of gravity, shrinking smaller and smaller, approaching but never quite reaching a singularity. At the moment of maximum compression, some new physics, perhaps quantum gravitational effects, kicked in and caused the contraction to reverse, producing a bounce that launched the expansion we observe today. The Big Bang, in this view, was really a big bounce, and our universe is the rebound from the death of a predecessor. The idea of an oscillating or bouncing universe has a long pedigree. It was discussed as far back as the 1920s, and the American physicist Richard Tolman explored cyclic models in detail in the 1930s. But these early models ran into a devastating problem rooted in the second law of thermodynamics. Entropy, the measure of disorder in a system, must increase with each cycle. A universe that goes through repeated cycles of expansion and contraction would accumulate entropy over time, meaning each successive cycle would be larger and longer lasting than the one before. Running the clock backward, each previous cycle would have been shorter and smaller, converging on a first cycle of minimal size and entropy, which brings you right back to a beginning. The cyclic model was supposed to eliminate the need for a beginning, but thermodynamics seemed to demand one anyway. Modern physicists have found potential ways around this problem. The most sophisticated versions of the cyclic model come from the work of Paul Steinhardt at Princeton University and Neil Turok, formerly at the Perimeter Institute in Ontario, Canada, and later at the University of Edinburgh. Their cyclic model, first proposed in 2001, envisions the universe as undergoing repeated cycles of expansion, followed by slow contraction, followed by a bounce back to expansion. The key innovation is that during each expansion phase, the universe grows by an enormous factor, diluting the entropy accumulated during the previous cycle. In a 2022 paper published in Physics Letters B, researcher Anna Eges and colleagues tracked the evolution of entropy and black holes through the cycles of this model, showing that the exponential expansion during each cycle effectively resets the conditions, diluting entropy density even as total entropy continues to increase. This means the universe can go through potentially infinite cycles without the entropy problem, leading to an absurd conclusion. However, the question of whether such a cyclic universe could truly be past eternal remains hotly debated. A 2023 analysis by researchers in the United States examined the general constraints on cyclic cosmological models and concluded that the very mechanisms designed to solve the entropy problem actually guarantee that the universe must have had a finite beginning. In other words, even a bouncing universe that cycles through expansion and contraction billions of times cannot have been cycling forever. There must have been a first bounce, a first cycle, a true beginning buried somewhere in the deep past. This conclusion remains controversial, and the debate between proponents and critics of cyclic cosmology is one of the liveliest in theoretical physics today. The technical underpinning for how a bounce could actually occur comes from an area of research called loop quantum cosmology, which is itself an offshoot of loop quantum gravity, one of the leading candidates for a theory of quantum gravity, the long-sought unification of general relativity and quantum mechanics. Loop quantum gravity was pioneered by physicists including Abhay Ushtekar at Pennsylvania State University, Lee Smolin, and Carlo Rovelli. When the principles of loop quantum gravity are applied to cosmology, the results are striking. In the standard Big Bang model, tracing the universe's history backward leads to a singularity, a point of infinite density where the theory breaks down. But in loop quantum cosmology, space itself has a discrete, granular structure at the smallest scales, the so-called Planck scale, approximately 10 to the power of -35 meters. This granularity means that the universe cannot be compressed below a minimum volume. As the universe approaches this minimum size, the attractive force of gravity is overwhelmed by a repulsive quantum geometric effect, and the contraction reverses into expansion. The singularity is replaced by a bounce. Martin Bojewald, a physicist now at Pennsylvania State University, was one of the first to show in 1999 that loop quantum cosmology naturally replaces the Big Bang singularity with a big bounce. His work, along with that of Ushtekar and others, demonstrated that the equations of loop quantum cosmology remain well-defined and finite, even at the moment traditionally associated with the singularity. There is no infinite density, no breakdown of the mathematics, just a smooth transition from contraction to expansion. In these models, the universe before the bounce was contracting, and our expanding universe is what emerged on the other side. Some versions of the model even suggest that inflation can arise naturally after the bounce, preserving all the observational successes of inflationary cosmology while eliminating the troublesome singularity. A different take on the cyclic universe comes from the British mathematical physicist Roger Penrose, who shared the 2020 Nobel Prize in Physics for his work on black holes. Penrose proposed a model called conformal cyclic cosmology, or CCC, in which the universe does not oscillate between expansion and contraction, but instead passes through an infinite sequence of eons. In each aeon, the universe begins with a Big Bang, expands, and eventually reaches a state of maximum entropy where all matter has decayed. All black holes have evaporated through Hawking radiation, and only a thin, cold bath of photons remains. Penrose argued that in this far-future state, the universe becomes so smooth and featureless that the distinction between large and small scales becomes meaningless. At that point, through a mathematical operation called conformal rescaling. The infinite future of one aeon can be identified with the Big Bang of the next. The death of one universe becomes the birth of another. Not through a bounce, but through a strange mathematical equivalence between the end and the beginning. Penrose went further and proposed a way to test this idea. If conformal cyclic cosmology is correct, then the evaporation of supermassive black holes in the previous aeon should leave behind characteristic hot spots in the CMB of the current aeon. He called these hot spots Hawking points, in honor of Stephen Hawking, whose work on black hole radiation made the prediction possible. In 2020, Penrose and his collaborators published a paper in the monthly notices of the Royal Astronomical Society, claiming to have found statistically significant evidence of these Hawking points in the CMB data. The paper reported the detection of numerous anomalous circular spots of elevated temperature, consistent with the predictions of CCC. However, the broader cosmological community has been skeptical. Independent analyses have reached conflicting conclusions about the statistical significance of the claimed detections. And as of the most recent assessments, the evidence remains inconclusive. The Hawking points are either a tantalizing hint of a previous universe or a statistical mirage in noisy data. And distinguishing between these possibilities will require better data and more sophisticated analysis. Another major approach to the pre-Big Bang question comes from string theory, the theoretical framework that attempts to describe all particles and forces as different vibrational modes of tiny one-dimensional strings. In one version of string theory cosmology, known as the ekpyrotic model, our universe is envisioned as a three-dimensional membrane, or brane, floating in a higher dimensional space called the bulk. The Big Bang in this picture was not an explosion from a singularity, but the result of a collision between our brane and another parallel brane. When the two branes collided, the kinetic energy of their impact was converted into the matter and radiation that fills our universe. Much like the way two cymbals crashing together convert kinetic energy into sound waves. The ekpyrotic model was developed by, among others, Steinhardt, Turok, Justin Curry, and Bert Overett, and it offers an alternative to inflation for solving the horizon and flatness problems. In the ekpyrotic scenario, the period of slow contraction before the brane collision naturally smooths out inhomogeneities and flattens the spatial geometry, achieving the same results as inflation through entirely different physics. The model does not require a singularity, and it naturally lends itself to a cyclic version in which the branes repeatedly collide, bounce apart, and collide again, producing a new Big Bang with each collision. The multiverse hypothesis, which emerges naturally from eternal inflation, takes the pre-Big Bang question in yet another direction. If inflation is eternal, meaning it continues indefinitely in most of space, even as it ends locally in regions like ours, then the universe as a whole is a vast, ever-expanding inflationary sea. And what we call our universe is just one bubble that nucleated within it. Other bubbles, other pocket universes, are continually forming, each with potentially different physical constants, different particle masses, different strengths of the fundamental forces. In this picture, the question, what happened before the Big Bang, has a straightforward answer. Inflation was happening before the Big Bang, and it has always been happening somewhere, producing new universes without end. Our Big Bang was simply the local end of inflation in our particular pocket of a much larger multiverse. The multiverse idea has a seductive appeal because it offers a potential explanation for one of the deepest mysteries in physics: the fine-tuning of the fundamental constants. The strength of gravity, the mass of the electron, the energy density of the vacuum. These and many other parameters of our universe appear to be exquisitely tuned for the existence of complex structures, chemistry, and life. If any of them were even slightly different, stars might not form, atoms might not be stable, and the universe would be a sterile wasteland. In a single universe, this fine-tuning seems like an extraordinary coincidence, the kind that cries out for an explanation. But in a multiverse where each pocket universe has different constants, the fine-tuning is no mystery at all. We naturally find ourselves in one of the rare universes where the constants are compatible with our existence, because we could not exist in any of the others. This reasoning is known as the anthropic principle, and while it has many critics, It is taken seriously by a significant number of physicists. The criticism of the multiverse is as fierce as its support. The physicist Peter Woit at Columbia University has been one of the most vocal skeptics, arguing that the multiverse is not a scientific theory at all because it makes no testable predictions. If anything is possible somewhere in the multiverse, then nothing is truly explained. The theory accommodates any observation, which means it is unfalsifiable. And unfalsifiable theories, by the standards of the scientific method, are not science. Other critics worry that the multiverse represents an abdication of the physicist's duty to explain why the universe is the way it is. Instead of seeking deeper laws that determine the values of the fundamental constants, multiverse proponents seem to shrug and say, "It's random and we got lucky." This debate is far from settled, and it touches on fundamental questions about the nature of scientific explanation and the limits of human knowledge. The American theoretical physicist Sean Carroll, based at Johns Hopkins University, has proposed an intriguing resolution to some of these tensions. Carroll has argued that the arrow of time, the fact that entropy always increases and time always seems to flow in one direction, may be a local phenomenon rather than a fundamental feature of reality. In his model, the universe as a whole exists in a state of high entropy, a kind of equilibrium. But it occasionally gives rise to low-entropy fluctuations that produce pocket universes like ours. Our universe began in a state of remarkably low entropy, the hot, dense, uniform state immediately after the Big Bang, and entropy has been increasing ever since, giving rise to the arrow of time we experience. But in Carroll's picture, our low-entropy Big Bang may have emerged from a higher-entropy parent space, like a bubble forming in a vast ocean. The parent space does not violate the second law of thermodynamics, because its overall entropy is high and increasing. The low entropy of our universe is a local fluctuation, a temporary dip in the entropy of a much larger system. This model elegantly sidesteps the entropy problem that plagues cyclic cosmologies while still allowing for the existence of pre-Big Bang physics. Alexander Vilenkin, a physicist at Tufts University in Massachusetts, has taken a different approach to the ultimate origin question. In a landmark 1982 paper, Vilenkin proposed that the universe could have originated through quantum tunneling from literally nothing, a state with no space, no time, no matter, and no energy. In quantum mechanics, particles can spontaneously tunnel through energy barriers that would be impassable according to classical physics. Vilenkin extended this idea to the universe itself, suggesting that the entire cosmos could have tunneled into existence from a state of absolute nothingness. This creation from nothing is not the same as creation from empty space. Because empty space is something, it has properties, dimensions, and quantum fields. Vilenkin's nothing is truly nothing, no dimensions, no fields, no laws, just the bare mathematical possibility of existence. The probability of such a tunneling event is extraordinarily small. But in a framework where probability is the only thing that exists, even an extraordinarily unlikely event will eventually occur. Vilenkin's model has been debated intensely in both physics and philosophy, with some critics arguing that the quantum mechanical rules governing the tunneling process are themselves something, so the creation is not truly from nothing. Regardless of these philosophical quibbles, the model demonstrates that modern physics can at least formulate the question of creation from nothing in precise mathematical terms, which is itself a remarkable achievement. Stephen Hawking and James Hartle took yet another approach with their no-boundary proposal, first put forward in 1983. In this model, the universe has no boundary or edge in time. There is no first moment, no singularity at the beginning. Instead, as you trace the universe's history backward toward the Big Bang, time gradually transforms into something more like a spatial dimension. Hawking described this using the concept of imaginary time, a mathematical technique in which the time coordinate is replaced by an imaginary number, which has the effect of converting the time dimension into a fourth spatial dimension. In imaginary time, the universe is a smooth, closed, four-dimensional surface, like the surface of a sphere, with no edge, no boundary, and no point that can be identified as the beginning. The universe simply exists the way a sphere exists, without needing a starting point or an edge. The no-boundary proposal eliminates the singularity by eliminating the boundary where the singularity would occur. It is an elegant idea, but it has proven extraordinarily difficult to verify or even to formulate rigorously. Recent mathematical work has raised questions about whether the no-boundary proposal is internally consistent, and the debate continues among specialists. While theorists have been developing these models, observational astronomy has been delivering surprises of its own that bear directly on the question of what happened at and before the Big Bang. The most dramatic recent source of surprises is the James Webb Space Telescope, or JWST, which was launched on December 25, 2021, and began full science operations in mid-2022. The JWST is the most powerful space telescope ever built, with a 6.5-meter gold-plated primary mirror and instruments sensitive to infrared light, allowing it to peer deeper into the universe, and therefore further back in time, than any previous observatory. The telescope was designed in part to study the earliest galaxies, those that formed within the first few 100 million years after the Big Bang, and its discoveries in this arena have been nothing short of astonishing. Within its first 2 years of operation, the JWST revealed galaxies at redshifts of 10, 11, 12, and even higher, corresponding to times just 300 to 500 million years after the Big Bang. Many of these galaxies were far larger, more luminous, and more chemically evolved than anyone had expected. In November 2024, an international team led by researchers at the University of California, Santa Cruz announced the discovery of 3 ultramassive galaxies, each nearly as massive as the Milky Way, already fully assembled when the universe was barely 5% of its current age. These galaxies, dubbed red monsters because of their red colors and enormous masses, contained stars that appeared to have formed extremely rapidly, challenging standard models of galaxy formation. According to the prevailing theories, galaxies grow slowly over time through the gradual accumulation of gas and the merging of smaller galaxies. There simply should not have been enough time in the first few 100 million years for galaxies this massive to have assembled. Their existence pushes the models to their limits and possibly beyond. Other JWST discoveries have been equally provocative. The telescope has found supermassive black holes, some with masses equivalent to hundreds of millions of suns, in galaxies that existed when the universe was less than 600 million years old. Standard models of black hole formation and growth struggle to explain how black holes could have become so massive so quickly. The JWST has also detected gravitationally bound star clusters in an arc of distant galaxies just 460 million years after the Big Bang, revealing that the processes of star formation and galaxy assembly were already far advanced at a time when the universe was supposed to be in its infancy. Some researchers have even detected signatures of heavy elements like oxygen, carbon, and nitrogen in these early galaxies, suggesting that multiple generations of stars had already lived and died, enriching their surroundings with metals within the first few 100 million years. All of this points to an early universe that was far more active, far more mature, and far more complex than anyone had anticipated. A small number of researchers have gone so far as to suggest that the JWST findings might challenge the Big Bang framework itself. Lior Shamir, a computer scientist at Kansas State University, published a paper in 2023 arguing that the properties of early galaxies observed by JWST are difficult to reconcile with the standard expanding universe model and might be better explained by alternative cosmological frameworks, including the tired light hypothesis, which proposes that the redshift of distant galaxies is caused not by the expansion of space, but by photons gradually losing energy as they travel through the cosmos. The tired light model was first proposed in the 1930s by the American astronomer Fritz Zwicky and was long ago rejected by most cosmologists because it cannot explain the detailed properties of the CMB, or the observed relationship between redshift and distance. Most physicists view Shamir's suggestion as a fringe position, and the overwhelming consensus is that the JWST discoveries, while surprising, do not overthrow the Big Bang. Instead, they reveal that our models of early galaxy and star formation need to be updated. The basic framework of the Big Bang, an expanding universe born from a hot, dense initial state 13.8 billion years ago, remains firmly supported by the weight of evidence. What is changing is our understanding of what happened in the first few 100 million years after the Bang. And the JWST is leading that revolution. However, some physicists have drawn a more subtle lesson from the JWST data. If structures formed much faster in the early universe than expected, this might have implications for the physics of inflation and the pre-Big Bang era. The fluctuations that seeded galaxy formation were generated during inflation, and their statistical properties are determined by the details of the inflationary model. If the early universe was more structured than the simplest inflationary models predict, this could mean that the inflaton field had features, bumps, or kinks in its energy landscape that produced extra power on certain scales. It could also mean that the pre-inflationary physics, whatever happened before or at the very beginning of inflation, left an imprint on the primordial fluctuations. In this way, the JWST's observations of the early universe are indirectly probing the physics of inflation and, potentially, the physics of the pre-Big Bang era. The CMB itself continues to be a gold mine for testing pre-Big Bang hypotheses. The Planck satellite, which operated from 2009 to 2013, produced the most detailed maps of the CMB ever made, measuring temperature fluctuations with a precision of a few millionths of a degree. These maps confirmed the predictions of inflationary cosmology in stunning detail. But they also revealed several anomalies that have never been satisfactorily explained. One is the hemispherical power asymmetry. The CMB fluctuations are slightly stronger on one half of the sky than on the other. In a universe that is truly isotropic, meaning the same in every direction, such an asymmetry should not exist. Another anomaly is the CMB cold spot, a region in the southern sky about 10 degrees across where the temperature is significantly lower than the surrounding areas. The cold spot is too large and too cold to be easily explained as a random statistical fluke. But no one has convincingly identified its cause. Some have suggested it might be the imprint of a collision between our universe and a neighboring bubble universe in the multiverse. A cosmic bruise left by a sibling universe bumping into ours. Others have proposed that it might be evidence of a supervoid, a vast region of below-average density that the CMB photons passed through on their way to us. The true explanation remains unknown, and the cold spot continues to tantalize cosmologists as a possible window into pre-Big Bang or extra-universal physics. Testing the predictions of loop quantum cosmology's bounce model has also become possible using the CMB. Bounce models predict specific patterns in the statistical properties of the CMB, particularly in a quantity called the bispectrum, which measures the three-point correlation function of the temperature fluctuations. A bouncing universe would leave a distinctive non-Gaussian signature in the bispectrum, a deviation from the purely random fluctuations predicted by simple inflationary models. Recent analyses using Planck data have searched for this signature and found no significant evidence of it, which places strong constraints on at least some versions of the bounce model. This does not rule out all bounce scenarios, but it does mean that the simplest and most natural versions of loop quantum cosmology's bounce prediction are not supported by the current data. The search continues, however, and future CMB experiments will have even greater sensitivity. The next great frontier in CMB science is the search for B-mode polarization, a specific pattern of polarization in the CMB that would be a direct signature of primordial gravitational waves generated during inflation. Gravitational waves are ripples in the fabric of space-time, predicted by Einstein's general relativity, and they were directly detected for the first time in 2015 by the LIGO experiment in the United States, which observed gravitational waves from the merger of two black holes over 1 billion light-years away. The gravitational waves generated during inflation would have much longer wavelengths and much lower frequencies than those detected by LIGO, and their signature in the CMB would take the form of a subtle swirling pattern in the polarization of the CMB photons, known as B-mode polarization. In March 2014, a team using the BICEP 2 telescope at the South Pole announced the detection of B-mode polarization, which was hailed as a landmark discovery and potential proof of inflation. However, subsequent analysis, including data from the Planck satellite released later that year, showed that the signal was likely contaminated by dust within our own Milky Way galaxy, and the claimed detection was retracted. The episode was a sobering reminder of how difficult these measurements are, but it did not dampen enthusiasm for the search. Two major experiments are poised to push the search for B-mode polarization to unprecedented sensitivity. CMB S4, short for Cosmic Microwave Background Stage 4, is a ground-based experiment planned for deployment in the Chilean desert and at the South Pole. Using an array of over 500 superconducting detectors to map the CMB polarization with far greater precision than any previous experiment. The project involves a collaboration of hundreds of scientists from institutions across the United States and has been estimated to cost over $800 million. Lightbird, a satellite mission led by the Japan Aerospace Exploration Agency with significant international participation, is designed to survey the entire sky in microwave frequencies with exquisite sensitivity to B-mode polarization. Lightbird is currently scheduled for launch in the late 2020s. If either experiment detects a clear B-mode signal from primordial gravitational waves, it would provide powerful evidence that inflation occurred and would constrain the energy scale at which it happened, telling us about physics at energies far beyond the reach of any particle accelerator on Earth. If no signal is found even at the sensitivity levels these experiments can achieve, it would rule out many of the simplest inflationary models and potentially open the door to alternative scenarios like the ekpyrotic model, which predicts a much weaker gravitational wave signal. Gravitational wave astronomy itself, beyond the CMB, may eventually offer a direct probe of the pre-Big Bang era. Current gravitational wave detectors like LIGO and Virgo are sensitive to waves from astrophysical sources like merging black holes and neutron stars. But future experiments could potentially detect a stochastic background of gravitational waves from the very early universe. The Laser Interferometer Space Antenna, or LISA, a space-based gravitational wave observatory planned for launch in the 2030s by the European Space Agency, will be sensitive to gravitational waves at much lower frequencies than LIGO, and it may be able to detect signals from phase transitions in the early universe or from the dynamics of cosmic strings, both of which are predicted by various pre-Big Bang models. Even more speculatively, proposals for third-generation ground-based detectors like the Einstein telescope in Europe and Cosmic Explorer in the United States aim to push sensitivity levels to the point where they could detect gravitational waves from the epoch of inflation or even from a pre-Big Bang bounce. These are long-term projects, decades away from completion, but they represent the ultimate tools for probing the origins of the universe. Particle physics also plays a role in the quest to understand the pre-Big Bang era, although its contribution is indirect. The Large Hadron Collider at CERN in Switzerland, the most powerful particle accelerator ever built, reaches energies of about 13 teraelectronvolts, or 13 trillion electron volts. This sounds impressive, and it is, but the energies involved in the Big Bang, and especially in inflation, are fantastically higher, on the order of 10 to the power of 15, or 10 to the power of 16 gigaelectronvolts. Trillions of times beyond what any conceivable accelerator could achieve. Nevertheless, particle physics experiments can constrain the properties of the inflaton field and other hypothetical particles associated with pre-Big Bang physics. For example, the discovery of the Higgs boson at CERN in 2012 confirmed the existence of scalar fields, fields that assign a single number to every point in space. And the inflaton is thought to be a scalar field. Studying the Higgs boson and searching for other scalar particles can provide clues about the energy landscape of the early universe and the mechanisms that might have driven inflation. The theoretical landscape continues to evolve rapidly. In addition to the models already discussed, there are exotic proposals that stretch the imagination even further. One is the idea that time itself has two directions, that the Big Bang was not the beginning of time, but rather a special moment from which time flows in two opposite directions. In this model, developed by Julian Barber, Tim Kozlowski, and Flavio Mercati, there is a universe on each side of the Big Bang, and in each universe, time flows away from the Big Bang. The inhabitants of each universe would perceive time as moving forward, away from the Big Bang, and would regard the Big Bang as their beginning, even though it is actually the middle of a larger, time-symmetric structure. This model is motivated by considerations of gravitational dynamics and the arrow of time. And while it is highly speculative, it offers a novel perspective on the nature of temporal directionality. Another speculative idea comes from the holographic principle, which emerged from studies of black hole thermodynamics and string theory. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that region, much like a hologram encodes a three-dimensional image on a two-dimensional surface. Some physicists have proposed that the entire universe is a holographic projection from a lower-dimensional boundary, and that the Big Bang corresponds to a phase transition or change of state in this holographic description. In one model developed by Niyush Afshorty, Robert Mann, and Razi Porasaan, the universe emerged from the collapse of a five-dimensional star into a five-dimensional black hole. And our four-dimensional universe is the holographic image projected onto the resulting event horizon. While this model is far from mainstream, it illustrates the creative extremes to which physicists are willing to go in their search for the truth about the Big Bang. Quantum computing represents a potentially transformative tool for tackling these problems. The equations of quantum gravity, loop quantum gravity, string theory, and other candidate theories of the pre-Big Bang era are extraordinarily complex, often involving infinite-dimensional mathematical spaces that are intractable for classical computers. Quantum computers, which exploit the principles of quantum mechanics to perform certain types of calculations exponentially faster than classical machines, may eventually be able to simulate the quantum gravitational processes that operated at the Big Bang or during a pre-Big Bang bounce. This is still a distant prospect. Current quantum computers are too small and too error-prone for such calculations, but the field is advancing rapidly, and researchers are already developing quantum algorithms specifically designed for problems in quantum gravity and cosmology. The philosophical implications of the pre-Big Bang question are as profound as the scientific ones. If the universe had no beginning, if time extends infinitely into the past through an endless series of cycles or an eternal inflationary process, then the question, why is there something rather than nothing, takes on a different character. There was never nothing, there was always something. The universe's existence becomes a brute fact, a foundational given that requires no further explanation. This idea is both liberating and unsettling. It liberates us from the need to find a first cause, a prime mover, a moment of creation. But it unsettles our intuition, which insists that everything must have a beginning, that you cannot have an infinite chain of causes with no first link. On the other hand, if the universe did have a definite beginning, whether through quantum tunneling from nothing, a first bounce, or the no-boundary proposal, then the mystery of existence takes on an even sharper focus. Why did the tunneling occur? Why does the wave function of the universe have the form it does? Why is there a mathematical structure that allows quantum tunneling in the first place? These questions may ultimately lie beyond the reach of physics, in the domain of metaphysics or philosophy, but they are the questions that drive the most ambitious physicists to keep searching. What is clear is that the era of treating the Big Bang as a wall, a boundary that physics cannot cross, is coming to an end. The tools and techniques for probing the pre-Big Bang era are being developed at an accelerating pace. Within the next decade or two, CMB, S4 and Lightbird will either detect or rule out the most straightforward signature of inflation, narrowing the field of viable models dramatically. The JWST and its successors will continue to reveal the nature of the earliest galaxies and black holes, providing indirect but powerful constraints on the physics of the first moments. Gravitational wave observatories will open entirely new windows on the early universe, and theoretical advances, driven by new mathematical techniques and the eventual maturation of quantum computing, will refine our models of quantum gravity and cosmological bounces to the point where they make sharp, testable predictions. The story of the pre-Big Bang era is still being written, and it may be decades before a clear picture emerges. But the progress of the last few decades has been extraordinary. We have gone from a position where asking about the pre-Big Bang era was considered meaningless, a question as empty as asking what lies north of the North Pole, to a position where multiple well-developed theories make specific, potentially testable predictions about what happened before the Big Bang. We have gone from a blank wall to a set of doors. And behind each door is a different vision of the deepest past, a bouncing universe. A cyclic cosmos, an eternal multiverse, a quantum tunneling event from nothing, a collision of membranes in higher dimensions, or a smooth no-boundary state where time fades into space. We do not yet know which door, if any, opens onto the truth. But the fact that we can even formulate these possibilities with mathematical precision is one of the greatest achievements of the human mind. The universe we inhabit is 13.8 billion years old, give or take a few tens of millions of years. Its age is written in the fading glow of the CMB, in the abundances of the lightest elements, in the distances and speeds of retreating galaxies, and in the slow tick of radioactive decay in the oldest rocks and meteorites. But the universe's age may not be the same as the age of existence itself. There may have been something before our universe, another cycle, another aeon, another bubble in the multiverse, and that something may itself have been preceded by something else, stretching back in an unfathomable chain of causation that our descendants may one day trace, but that we can only dimly perceive. Or there may have been nothing, a true void from which the cosmos sprang without cause or precedent, a mystery so deep that it will forever exceed the grasp of any theory or equation. Either answer, infinite regress or absolute beginning, is staggering in its implications. And the fact that we are alive to contemplate it, that matter has organized itself into beings capable of asking where it came from, is perhaps the most astonishing feature of the universe, regardless of how it began. The next time you look up at the night sky and see the stars, remember that the light reaching your eyes has traveled for years, decades, centuries, or even millennia to reach you. The most distant light you can see with the naked eye comes from the Andromeda galaxy, about 2.5 million light-years away, meaning you are seeing it as it was 2.5 million years ago. But the CMB, invisible to your eyes but detectable by radio telescopes, comes from 13.8 billion years ago, from the very edge of the observable universe. And behind that edge, behind the veil of the CMB, there may be a story even more ancient. A story of universes being born and dying, of space-time folding and bouncing, of quantum fields fluctuating in the void, of brains colliding in dimensions we cannot see. That story is the one that physicists are now learning to read, letter by letter, equation by equation, observation by observation. It is the greatest detective story ever undertaken, and its final chapter has not yet been written.